this is sort of the tail end of the ideas of limiting and excess. And I want to congratulate you guys because this is the first year I've ever taught this when not a single person made the mistake that this bullet point was intended to address. Nobody did it. It's awesome. Nobody in either class, not a one of you. You're comparing the reactants. And every year somebody does a factor label of a reactant over to a product and then tells me the limiting. And I'm like, that doesn't work. None of you did it. So you know that you're just comparing the reactants. Your factor label is reactant to reactant. And you guys all got that. Mole ratio of reactant to reactant, you've got that. I think you guys have this. So those of you who had some errors, for the most part, seem to get where you need to go. So that's a good thing. You ever made cookies? Delicious, wonderful, maybe chocolate chip cookies. Maybe with walnuts in them. Sounds pretty good, huh? So you're making chocolate chip cookies, and the recipe says you should get 2 dozen cookies out of this. Yum. But after you've baked them all, and we're assuming that all these cookies are uniform size and you didn't do something ridiculous like use an ice cream scoop as a cookie dough scoop. When you're all done, you only have 1 dozen cookies. Now, I don't know if any of you are cookie dough eaters or have family or friends who are cookie dough eaters. I love cookie dough. So, I don't know what happened between putting all the ingredients in the bowl, combining it, and getting a dozen cookies, but something happened. What percentage of the cookies that you should have gotten did you get? 50%. You got half the cookies you should have. And this here was what we should have gotten. This is what we actually got. So you figured that out in your head by taking what you actually got divided by what you should have gotten. Okay. And furthermore, you did another step in your head that you weren't aware of. You multiplied that by 100. Okay. It's easy. Well, what that 50% is your percent yield for your cookies. So now we're going to talk about percent yields in the sense of chemical reactions. And it's really not much more complicated than this. So percent yield is just a relationship between what you should have gotten and what you did get. And the theoretical yield is the maximum amount of product that you should be able to make. Okay? The theoretical yield is your should have gotten. Okay, that's terrible. I apologize. Let's get rid of that color. The one button I wish they had on here is that's even worse. Okay, so your theoretical yield is your should get. Now, we don't live in a perfect world. We've talked about this. And there are lots of things that can happen in a chemical reaction. Lots of things can go wrong between putting all the reagents together, heating, stirring, whatever, and measuring your product. So we have what's called mechanical loss. If you've ever baked a cake, and as you take the batter out of the bowl, if you just dump the batter into the bowl and don't scrape the bowl, you have a lot of mechanical loss. Often when you're running a reaction, you get mechanical loss, and it's the same kind of thing. You didn't scrape down the sides of your evaporating dish. You didn't thoroughly wash your Erlenmeyer flask. So things like that happen. All the percent yield is that actual yield, so what you really got, divided by what you should have gotten. So let's do the simplest possible example that we can. I give you a reaction where you should be able to produce 257.2 grams of ammonium nitrate. Okay. You have all the reagents to produce that much ammonium nitrate, but when you're all done, what you have, in fact, is only 242.3 grams of ammonium nitrate. What's your percent yield? So we get 94.20684, etc. When we sig fig it, and we can have 4 sig figs, 94.21% yield. Okay, and that would actually be a pretty respectable percent yield in a high school chem lab. It's not great. It would get you a redo in a quantitative analysis chem lab, but it's a reasonable yield. Okay, so those are really easy. Let's do one more like that, and then we're going to move on to something a little bit more challenging. Okay, so I give you all the reagents that should allow you to make 8.31 grams of calcium chloride. You run your reaction, you separate out all of your products, which probably involves filtering, maybe evaporating off liquid, and you come back and you tell me that you made 8.54 grams of calcium chloride. Do we have a problem, Houston? Okay. Can you calculate a percent yield here? Yes, you can, so do it. My percent yield is greater than 100. What happened? Created mass. I'm an alchemist. Magic. Violated the fundamental laws of the universe. Now, among the other things, if you remember back to the lab where you did physical separations, I had a few groups that created mass. What typically happens? We didn't dry our stuff well enough before we masked it. A dead bug fell into our stuff. We spilled our stuff on the table and we swept it up and we think there might be chunks of who knows what in there. You know, anything can happen. So you can have more than 100% yield, but it definitely means you screwed up. It definitely means that there's a serious problem with your process. So any number of things can be an explanation for that, but it can happen. You can mathematically say, yeah, we have 102% yield, we have 103% yield, but it's a pretty clear red flag. Okay, so these are the easy examples. Let's do something that's a little bit more interesting. So what I've done here is I've given you an equation, and this should look familiar to you. It was on your quiz this morning. 3 moles of magnesium oxide, 2 moles of aluminum, gets you 3 moles of magnesium and a mole of aluminum oxide. If I tell you that I'm going to give you 265 grams of aluminum, and you produce 228.9 grams of magnesium, what's your percent yield? Pardon? 328, sorry, what did I say? Okay, sorry, 328.9 grams of magnesium. What's your percent yield? Have I given you a theoretical yield? Have I given you an actual yield? Are you a little bit puzzled about what I've given you? Okay, good, let's talk about it then. So, obviously this is one of our products, and we're looking at percent yield, so we're looking at products. You managed to get 328.9 grams of magnesium. That's what you got. Therefore, that is your what? Actual yield. Okay. Do you have your theoretical? Do you have the means to figure out your theoretical? Yes. So what we're going to do at this point is take this given, and you guessed it, we're going to do a factor label to figure out how much magnesium we should be able to make. So now we have a number which is our theoretical yield. So now we have the means to do a percent yield problem. Okay? Okay, so our raw answer is going to be what? 91.8298. It goes on and on and on percent. Where do we get our sig figs for this? What is the lowest number of sig figs in our given that we've used? 3, because this 265 forms the basis of that number. So we have to go all the way back to that first step because we used that as a given. So we can only have 3 sig figs, so this is 91.8% yield. And that's, in a high school chemistry lab, that's respectable. It wouldn't make me go, oh my gosh, but it wouldn't make me go, wow, you guys did a great job. It's fine. It's okay. It happens. Okay, so not so hard, right? Let's do one more like this. Okay, so you've got the same equation. We're still working with 265 grams of aluminum. But now we're looking at aluminum oxide as a product. And it's the same exact situation. We set up a factor label going from the mass of our given to the mass that we should be able to produce of the aluminum oxide. Okay, so we're back in that situation, aren't we? Let's identify, where's our actual yield? Yeah, it's given in the problem here. So that's our actual. Our theoretical is actually a little bit lower. So we're back in the situation of we've obviously screwed something up, we've gained mass. Let's go ahead and do the percent yield. So we get a raw number of 102. When we sig fig, we're back to 3, so 102% yield. Some of the common explanations for this. Maybe when we separated out our aluminum oxide, we didn't actually get all of the magnesium out of it. And so the mass that we're getting is a combination of the two products. That's a common one, so you didn't clean one product well enough. That would then lead to, if we looked at percent yield of magnesium, we'd get less than 100%. So you can look at it that way. You can say, well, what's my total percent recovery? If you've got loss on both of them, okay, then you just lost some material. If you've got gain on one and loss on the other, you may not have cleaned one well enough. If you've got gain on both of them, you have a dead bug in there, or something, something weirder than the normal explanations. Okay, so to recap, anytime you see something where you're given the mass of a reactant and the actual mass of a product, you're going to do the percent yield by figuring out your theoretical using whatever mass of reactant you have. Reasonable? Straightforward? Okay. So tomorrow we'll pick up with percent yield problems where we have to figure out the limiting and excess reagent first. We'll leave it here for now, and I'll hand you your practice sheets.